Hey everyone, and welcome back to the Foundry by Forge College. Today we're diving into deployment challenges and security in Cloudbreak integration. Now, in our last explainer on designing integration workflows for Cloudbreak, we kind of spent our time in this beautiful, utopian dream world, right? We designed these perfect, pristine, replay-safe integration workflows. We smoothly mapped incoming on-chain state change events right into a reliable processing pipeline. But, well, today we're waking up. We're moving from the perfect theory of that last lesson into the messy, unpredictable reality of actual server deployments. So grab your detective hats, because we've got some bugs to hunt.
Look at the stark contrast mapped out here on our blueprint. On one side, you have our theory, those perfect idempotent workflows where handlers can be rerun safely without producing duplicate side effects. We used deterministic keys and a compact change journal, and honestly, it was elegant. But then, on the other side, we have reality. This is where we crash headfirst into deployment friction and failures. We're talking about real-world issues like permission gaps, observability blind spots, and storage backend mismatches, the kinds of things that can silently break those beautiful idempotency guarantees we were relying on.
So here's a quick look at our debugging game plan for today's explainer. First, the reality of deployment. Second, the read-after-write mystery. Third, investigating diagnostics. Fourth, fixing configuration drift. Fifth, the defense of retry. And finally, building the debug report.
All right, jumping right into part one, the reality of deployment. This is exactly what happens when perfect code meets messy environments.
We're starting our investigation right at the crime scene. Why do perfectly designed handlers suddenly break when you put them in a live environment? Well, the answer almost always comes down to untested assumptions. And the absolute worst offender here, configuration drift. It's basically the phenomenon where an environment's actual runtime configuration slowly, over time, diverges from its expected documented state. You can think of it like a mischievous gremlin sneaking into your servers in the middle of the night to slowly turn dials and tweak settings. Your code hasn't changed at all, but the ground underneath it has shifted, causing these spectacular, yet totally silent, failures.
Moving on to part two, the read-after-write mystery. Time to set up the simulator.
Okay, so picture this. We fire up our simulated local Cloudbreak environment, and immediately, bam, we hit this terrifying inconsistency in our state handlers. Look at this sequence because it is incredibly frustrating when it happens to you in the wild. Step 1, your system writes the state. Step 2, your system immediately attempts to read that state back. Step 3, you receive stale, outdated data. No way, right? This read-after-write bug is literally like dealing with a terrible waiter who forgets your order 3 seconds after you place it. You just told them you wanted the soup, you ask when the soup is coming, and they look at you blankly and go, "What soup?" In a distributed system, this happens when data just hasn't fully propagated or settled in the storage layer before your read request hits.
Part 3. Investigating diagnostics. Let's collect the evidence. As you've probably heard in a lot of the wider programs at Forge College, observability is absolutely crucial in software engineering. I mean, we literally can't fix what we can't see. So our first job as technical detectives is to collect hard, undeniable evidence of this failure. We run our cargo test against the simulator in a strict mode and capture the fallout. You're going to want to gather these 3 specific artifacts right into a diagnostics folder. First, the simulator logs, which tell us what the server thinks happened. Second, the integration logs, which tell us what our handler experienced. This is where we'll actually see the panicked back-off sequence. And third, the simulator's config.yaml file. Honestly, this file, it's the smoking gun.
Okay, part 4, fixing configuration drift, strict mode versus lenient expectations. Let's do some deduction here and compare these settings. Our integration code was written expecting the lenient mode values on the right side of this table. It expected a persistent write-through cache, like a massive 512 megabyte walk-in closet with 0 compression, meaning data is instantly accessible. But the simulator, it's running in strict mode on the left. It forced our environment into a tiny 128 megabyte gym locker and applied heavy ZSTD compression. So the cache evicted data way too fast, and the compression meant reads were delayed until compaction finished. This mismatch right here is exactly why our waiter forgot the soup. The storage engine's behavior totally diverged from what our code assumed. So, how do we actually fix this? Well, we apply configuration hardening. We go into the simulator's config.yaml, we align the column family options to remove that compression, and we bump the cache eviction threshold back up to 512 megabytes. Once we edit that, we restart the simulator so it picks up the changes and run our cargo test again. We are actively stamping out that configuration drift.
Part 5. The defensive retry, layering our mitigations.
Now, here is a hard truth about distributed systems. What if correcting the drift reduces, but doesn't completely eliminate, the intermittent failures? Well, we layer our defenses. We apply a code patch that introduces exponential backoff. So instead of just failing immediately when the waiter forgets our order, or asking repeatedly at the exact same speed, our system actually waits. 100 milliseconds for the first retry, 200 for the second, 400 for the third, 800 for the fourth. We wait just a bit longer between each bounded reread to ensure the write has fully settled in the storage backend. We're verifying those right timestamps and gracefully handling transient delays rather than just throwing a massive fatal error.
Finally, Part 6. Building the debug report. Documenting the resolution.
Okay, with our configuration hardened, our defensive retries in place, and those gremlins finally banished, our validation script returns a beautiful, clean exit status of 0. But look, a fix doesn't really exist until it's documented. Your final debug report artifact has to contain these 3 concrete sections. First, the prefix evidence. You need at least 10 log lines showing the failing read, keys, and timestamps. Second, mitigation steps. Show the exact configuration diffs and the retry patch you applied. And third, the validation output, the final script results proving it actually works. You do this so that any peer on your team can reproduce both the initial failure and your brilliant fix. It's what makes your solution repeatable and verifiable.
If you remember absolutely nothing else from this explainer, remember this quote right here. Treat configuration as first-class code. Seriously, the ultimate takeaway from our debugging journey today is that settings, cache sizes, and flags are just as vital as your Rust or integration logic. You have to record expected values, automate their propagation, and include configuration checks in your CI pipeline to always catch drift early.
To wrap up this module of Cloudbreak, exploring Solana state storage, you've successfully navigated the messy reality of deployments and brought order to the chaos. But I want to leave you with a question. What undocumented gremlins are silently altering configurations in your own live environments right now? To continue your learning journey on advanced Solana concepts and explore more real-world deployment case studies, visit forge.college. Thanks so much for watching. Keep those configurations locked down, and I'll see you in the next explainer.